Greetings! Welcome to Electronic Circuits 1. I am Behzad Razavi, and this is lecture number 34. Today we will continue to develop the large signal and small signal models of MOS devices and see how they are used in circuit analysis. But before we go there, let's take a look at what we covered last time. In lecture number 33, we realized that if the gate source voltage of a MOS device is incremented by an amount delta V, then the drain current is incremented by an amount equal to Gm times delta V, where Gm is the transconductance. So we simplified the circuit to this notation. We realized that here this voltage source shows only the increment. For example, the microphone signal that we added to the battery voltage already present between the gate and source. So as far as changes in the signals are concerned, we eliminated that battery and we just considered one voltage source representing a change in the voltage. In a sense, this voltage source represents the microphone itself. If I don't speak to the microphone, there's no change in the voltage here. We still have the original battery between the gate and source to bias it up, but there's no signal going in. All right, so based on that, we realized that we can build a small signal model. The small signal model is different from large signal model in that it assumes or it regards only changes in the signals. Changes in voltages, changes in quantities such as voltages and currents. And these changes are usually created by signals. So when a microphone signal comes in, it changes VGS, it changes ID, etc. And the small signal model only represents the changes. So this is what we have observed. We saw that if we have the ID VGS characteristic of a MOSFET, and then we come along with a microphone signal, which is plotted as a function of time this way. We see that the microphone signal is modulating VGS, right? It's changing VGS around a bias value V0. And in response to that, the drain current of the MOSFET also changes. Now, we can have a case where the change in VGS, this change here, and the change in ID are large. You can see here that if I go up here, I get very little ID, and if I go up here, I get a lot of ID. So ID fluctuates a lot. That is large signal operation, and for that we would have to use the large signal model, meaning ID is equal to 1/2 of mu NC ox W over L VGS minus VTH squared, maybe 1 plus lambda VDS, all of that. On the other hand, if the signal that's coming in is small, for example, this green waveform here, so that we negligibly perturb this VGS or this drain current, so drain current only fluctuates between here and here, then we can use the small signal model. The small signal model says that the drain current fluctuation, delta V, is equal to the VGS fluctuation, delta V, times the slope, which is the transconductance, right? So the small signal model comes out to be as simple as that. The gate source change or fluctuation goes between gate and source, is applied there, and the current change is represented by Gm delta VGS. All right, so this is what we call the small signal model of the transistor. And in fact, oftentimes, instead of delta VGS, we just write one voltage, and usually with lowercase to indicate that it's small signal. So we might, instead of delta VGS, we might just write V1, lowercase v1. V1 is the voltage that we measure between here and here in the small signal model. It's a time varying voltage. And then this would be just Gm times V1. It's just a notation. Instead of saying delta VGS every time, we just call it V1. V1 is really the change in VGS. All right, so today we'll try to expand upon these things, both large signal and small signal models, and try to understand these a little better by means of some examples, etc. So today we'll look at these models more, and then we go and see how channel length modulation may affect our models, because in these models I have implicitly neglected channel length modulation. And then hopefully we'll have time to look at a different type of MOS device, which we call a PMOSFET. All right, so let's talk about a large signal and small signal models. I go over these over and over again. I take my time and go over these slowly because I know oftentimes students have difficulty with these concepts. So we just repeat and repeat until they become second nature and we are comfortable with them. All right. So we saw that we have a small signal model for the device, and I'm going to draw that here. So the large signal model looks like this. So the device has a gate, a source, and a drain. And again, we're not worried about the effect from the substrate. And we are only concerned with these models in the saturation region, not in the triad region. As I said, in most of the circuits we study in this course, our circuits are in saturation, our devices are in saturation. Okay, so if we are in saturation, the large signal model is given by this simple model, and this current source is given by 1/2 mu n C aux W over L VGS minus VTH squared. And if you want to include channel length modulation, 1 plus lambda VDS. All right, that is the large signal model. Okay. Now, for small signal purposes, meaning if the signal that's coming in is small, we can simplify the model to this. So here's the signal, the source, and the gate, and then here we have something like this, which is Gm times V1. Now, if you remember from last time, our analysis usually has to draw upon both of these, because when we start looking at the circuit, first we have to see what bias voltages and what bias current it has. For that calculation, we still have to use this model, even though there's no signal in the circuit. So this model would apply to a situation like this, where we have a constant battery between the gate and source, another battery between drain and source. So we know these batteries, we know VGS, we know VDS, we can go ahead and find the current. And that gives us all the bias conditions of the device. Now, that's done. We have the properties we need. We can find GM, because GM can be calculated in terms of VGS minus VTH or ID, all the equations that we saw before. All right. Now that we have GM, we say, okay, if in the circuit a signal comes in, for example, apply between these 2 points, then I make a representation for only the signal. And that representation is like this. Let's call the signal something like this, V in, lowercase, to indicate it's a small signal. And then, for example, I'm interested in this current, ID. That's also lowercase. Now, if I'm interested in voltage change, so I have a microphone signal here that modulates this VGS, and as a result, this current also has modulation fluctuation, I just look at the fluctuations. I forget about the bias quantities. So here's the fluctuation of the voltage between gate and source. Here's the fluctuation of the current. And these are related by this model. Okay, so as an example, let's go ahead and construct a model for, well, let me make one more point and then I'll go over an example. Okay, now in our circuits, we often encounter constant sources, constant voltage sources like batteries, constant current sources. So the question is, when we are constructing a small signal model of a general circuit, we know that, of course, we replace the MOS device with this. What do we do with the constant voltage sources and current sources? So small signal model of constant sources. Well, you have got to remember that a small signal model represents time-varying quantities, time-varying voltages, time-varying currents. All right? So if a quantity does not vary with time, it means its time change is 0. And if it is 0, in the small signal model, it's set to 0. So in the small signal model, any source that is constant with time, meaning its change with time is 0, has a 0 value in the small signal model. So if we have a battery, and the battery has some voltage on it, V1, but it's constant with time, because its change with time is 0, it becomes a 0 voltage source in the small signal model. What does that mean? Well, we have to find a 0 voltage source. We know that a 0 voltage source is equivalent to a wire, a short circuit. So that becomes a short circuit. Only a short circuit can guarantee that the voltage difference from here to here is 0. How about the current source? If we have a constant current source, then when you set it to 0, again, it doesn't change with time. So in the small signal model, it has to become 0. When we set it to 0, it becomes an open circuit. And of course, it is only an open circuit that can guarantee 0 current. So that becomes an open circuit. So long as we remember these, and so long as we have this model for the MOS device, we can build the small signal model of any circuit that's given to us. So let's go ahead and look at an example. Okay, suppose we want to draw the small signal model of this circuit here. Now, we don't know what the circuit does, and that's okay. We're not interested at this point. But we have a microphone, a battery, and then another battery up here. Remember, we talked about these before. So here's V1, here's V0, RS, RD. And we can call this transistor M1. We call MOS devices by M, M1, M2, etc. All right, so this is the overall circuit given to us. It has everything. And we would like to construct the small signal model of the circuit. Okay, well, we can start from here and move towards the right. Make our way towards the right. We model this microphone for now by only a simple time-varying voltage source. So this microphone is just a time-varying voltage source. We may call it Vin with lowercase, again, to indicate small signals. So that is the input voltage source. All right, so we begin with that. Does this change with time? Yes, so it has to stay in the small signal model. So here's the model for that. Now we go to this guy. Does this change with time? No. If it doesn't, then it has to be replaced with a 0 voltage source, a short. So here's a short circuit. And go over here. We see the MOS device. The MOS device under small signal condition. Well, here's the model. So we place the model between the gate and the source and the drain, as you can see here. And this is GMV1. And there's a resistor RS between the source and the bottom terminal. There's a resistor from here to here, so I have to include that between the source and the bottom terminal. Then what do I have? I have a resistor RD going from drain to this top rail here. So let's put that here, RD. And now I have to replace this battery with a small signal model. The battery voltage doesn't change with time, so it becomes a short circuit. So we have a short circuit all the way down here. This is the small signal model of that circuit. What it does, we don't know, but that's okay for now. All right, so a few notes. Number one, you might be uneasy with the notion that this is an open circuit, but it has a voltage on it. But that's perfectly fine. we are not violating any physical laws or any circuit laws by having a system like this. All right, so don't be confused, don't be uncomfortable that there's nothing here between these two, but there's a voltage on it. That's fine. You don't have, if you just take a battery, two wires to connect to a battery and just hold them like this, they have a voltage difference, but they're not connected to anything. So that's perfectly fine. Number two, notice that in this particular circuit, V1, the gate source small signal voltage, is not equal to the input voltage, right? Because there's this resistor has some current maybe through it, all sorts of things. So we cannot say that V1 and Vin are equal. Just so that you remember, that means that not in all circuits do we have VGS equal to the input voltage. All right. Let's go ahead now and look at the effect of channel length modulation. Now we know that when we change the drain source voltage of a MOS device, its current changes. So if I change this voltage here, this current changes, even though VGS is constant, because we saw that the pinch-off point near the drain keeps going towards the source. The actual length becomes a little shorter, so the current increases. So now we are wondering if this effect, channel length modulation, impacts this small signal model. Okay, so let's try to formalize how we construct a small signal model for a given device, a MOSFET or anything else. And then, based on that, go ahead and revisit the small signal model of the MOSFET. All right, so here's the general procedure. For constructing a small signal model of anything that you want. Any device you are interested in, you can follow this procedure to build a small signal model for. All right, so in the first step, what we do is we take two terminals, any two terminals we want, and apply a voltage difference between these two terminals. All right, so apply a, okay, sorry, let me take a step back here. I think I should reword this to make it less confusing. All right, so apply proper bias voltages to the device. Okay? So we know that the device has to be biased. If the device is not biased, it's dead, so there's no point in constructing a small signal model for it. Okay, so for example, for a MOSFET, we said we need a sufficiently positive difference between the gate and the source voltages, right? So that we exceed the threshold, we extract a channel, now we can conduct current. And then we also saw that the source, the drain source voltage cannot be too small, otherwise we go into the triad region. So we also need some voltage here to guarantee that we are in saturation. Okay, so now we have these values. All right, the next step, we go ahead and increment one of these voltages, only one of them, not two, not more. It's important to remember that. So increment one of the voltage. Okay, so let me write this a little better. Increment the voltage difference between two terminals So between only two terminals, for example, this voltage source between these two terminals, or this voltage source only between these two terminals, only one at a time. All right. Measure all current increments. So as a result of the voltage that we just changed, for example, we change this V0 by some amount, it's possible that some currents change. Maybe, maybe not. So whichever changes, that's what the one we look at. All right, so we measure those changes. And then in the last step, model this change by a proper electrical device. And by that we mean resistors, maybe voltage source, current sources, voltage sources, that sort of thing. Okay, so we have already done that, for example, for GM, right? For the, I should say for this simple small signal model that we derived. Because what we did was, we said if this voltage changes by delta V, right? If this changes by delta V, so if this goes to V0 plus delta V, then we saw that this current changes from ID to ID plus GM delta V. All right, assuming everything is small. And we said, okay, I changed this voltage by delta V, and I measured all current changes. Well, the gate doesn't have any much current, so we don't have to worry about that. The only current is really between drain and source, and that current changed by GM delta V. So I followed all of these steps up to here. In step 4, I said I will model that by some proper device. So how should I model that? Well, we know that the device is in saturation, so we are going to model that by a voltage-dependent current source. And we call that GM delta V, or as I said before, GMV1. So if this is delta V, then that is the model that we have developed. So between gate, source, and drain. All right. Why should this be a voltage-dependent current source? Can it be a resistor? No, because the problem is that we are applying a voltage change over here between two terminals, and we are measuring a current way out here. The only time we can use a resistor is if the voltage and the current are exactly belong to a two-terminal device, right? Like a resistor, you apply voltage across it, you measure current through it, then those two are related by Ohm's law. But if I apply voltage here or a voltage change here, and I am not measuring a current change here, I'm measuring current change over there, that cannot be modeled by a resistor. It has to be modeled by a voltage-dependent current source. And that's what we have done. Okay, so that's our procedure. Now, so far, because we have concerned ourselves with a gate source voltage change, and we looked at the drain current change while VDS is constant, we did not feel channel length modulation. Channel length modulation manifests itself only when this drain source voltage begins to change. But we never changed it, so we never saw it. The model doesn't know anything about it. But our construction is not finished yet, because we said increment the voltage difference between two terminals. So we have to do this for every two terminals and see what we get. In the next step, what we have to do is keep this voltage constant, and now go ahead and increment this voltage. And again, measure all the changes in all the currents, and then see what we can do to model them properly. All right, so let's go ahead and do that. Here's the situation. I have a MOS device with a constant gate source voltage, but now I go ahead and increment the drain source voltage. So this used to be VDS. Now it becomes VDS plus delta V. Right, according to this step here. And now I need to measure the change in all the currents. Well, again, the gate current doesn't change much. It's very small anyway. So we're really concerned with the drain current change. So that current goes from ID to ID plus delta ID, because we changed the drain source voltage. All right? Okay, so first we have to measure how much change we have, right? That was the step number 3. And then we have to see how that can be modeled. If you have a delta V change here and delta ID change here, is that a voltage-dependent current source? Is that a resistor or something? If in doubt, you can always assume a voltage-dependent current source. But in some cases, it's simpler. It reduces to, for example, a resistor. Okay, so let's go ahead and do that. Just remember this picture. I will go to a new page, and I will try to derive a delta ID in terms of delta V. All right, so we write ID plus delta ID. The new current is equal to 1/2 of mu n C ox W over L VGS minus VTH squared 1 plus lambda. So we used to have only VDS. Now we went from VDS to delta VDS plus delta V. So this now has VDS plus lambda delta V in it. Okay, that's exactly what happens in the circuit that we had there a minute ago, right? We are just looking at the general case. We have a battery between gate and source. We have a battery between source and drain, and we increment that battery by delta V. All right, this is the general equation. This is large signal model, if you will. Even though the changes are small, I start with the general equation. Okay? If you remember last time when we derived GM, we also did the same thing. We assumed that this VGS incremented by delta V and then simplified things, and came out, the GM popped out. So it's the same situation here. Okay, let's expand this side and see what we get. 1/2 of mu n C ox W over L VGS minus VTH squared times 1 plus lambda VDS. Do we recognize that? Well, that's just the bias current of the device, so that's ID. So we have ID plus 1/2 of mu n C ox, the rest of the stuff, so 1/2 of mu n C ox W over L VGS minus VTH squared 1 plus lambda delta V. All right, so this ID cancels with this ID. I'm sorry, I don't have a 1 there. Let me erase this. Okay, so we already used that 1 plus lambda VDS for this to get ID, so all that's left is lambda times delta V. Okay. All right. Well, let's try to calculate delta V over delta I. Delta V over delta I is equal to 1/2 of mu n C ox W over L VGS minus VTH squared times lambda. Okay, sorry, that's the other way around. So I'll just say minus 1 here, or maybe the other way around. Let's see. Erase this, and minus 1. Okay, we'll make an approximation now. We will say 1/2 of mu n C ox W over L VGS minus VTH squared is approximately equal to the drain current. The actual drain current is all of the stuff up to here, right? We just drop out the 1 plus lambda VDS factor, and we say this is approximately ID. So this is approximately the bias current, which tells me that delta V over delta I is approximately equal to 1 over lambda ID. All right. Okay. Now, what does this mean anyway? Well, we have a special case here that allows us to not use a voltage-dependent current source. So here's what we've done. We incremented this voltage source by some amount, delta V, right? And in response to that, we saw that the drain current changed by delta I. This current changed by delta I. But it just happens that that delta I is flowing out of this battery here, right? Same thing. So if I put all of this in a black box, I have two terminals, right? And what I see is that when the voltage applied between these two terminals increases by delta V, the current flowing to these terminals increases by delta I. Well, how can I model this? Just a resistor. That's exactly what a resistor does. I don't need a voltage-dependent current source. So we will model this by a resistor, and we'll call it RO, output resistance of the MOSFET. This gives us the following small signal model. We have GM, so let's call this again V1 for simplicity. V1 represents the increment in the gate source voltage. And then here we have just a resistor, RO, GMV1. This is the drain, this is the gate, and this is the source. So that's very simple. That's what we can do anytime we have a transistor, a MOS transistor. Now, this is always a question. When do we include channel length modulation in the large signal calculations or bias calculations, and when do we include it here, etc.? And the general answer is the following. When we want to do bias calculations, so I have given you this voltage and this voltage, I'm asking you to find the current and all that, we typically neglect channel length modulation. And then when it comes to small signal model, our first reaction is to neglect channel length modulation and proceed. We go ahead to the calculations for the circuit, whatever is of interest to us, and then see if the results are sensible. If not, we come back and include channel length modulation. Sometimes it takes experience, a lot of practice to see under what conditions channel length modulation is negligible or not. And that's what engineering is about. You have to develop that sense of when we can make what approximation. All right. So based on this model, now we can analyze various circuits. Now, remember we had three equations for GM before? And they were obtained by taking the derivative of the large signal model with respect to VGS. But in that large signal model that we used to derive GM, we did not include lambda VDS, if you remember, right? So we neglected channel length modulation, we found GM, and we used it here. So now the situation is a little more complicated, right? Because we see that GM itself may also be affected by channel length modulation. Because I have to take this equation up to here, and then take the derivative with respect to VGS. But what we'll do in this course, not in graduate courses, but in this course, is neglect that. So we say we neglect the effect of channel length modulation on the GM expressions. In other words, we continue to use those expressions for GM even though we know they may not be quite accurate. All right, this is just to simplify things. Okay, so let's look at an example. Let me change the color of my pen. So here's an example. Suppose we have a MOSFET like this, and I have biased it up. So I have applied 1.2 volts here between the gate and the source. I have applied 1 volt here between the drain and the source. And here are the parameters of the device. Mu n C aux is 100 microamps per volt squared. The threshold of the device is 0.5 volts. A lambda is 0.2 inverse of volts, strange unit. And then what else? I think that's all we need. Okay. And we would like to write out or derive the small signal model of this device. But before we get excited, the question is this transistor in saturation or not? Because all of these models are correct for saturation. So I will give you 90 seconds to figure out if this MOS device with these parameters is in saturation or not. All right, so is it in saturation? Well, we just remember for saturation to be guaranteed, we have to have VGS minus VTH, which is the overdrive voltage, to be less than or equal to VDS. In other words, VDS has to be large enough. If it's too small, then at some point the device will be in triode region. Okay, well, let's see. Is that true? 1.2 volts minus 0.5 volts is 0.7 volts. So the overdrive is 0.7 volts. And VDS is 1 volt. So that's great. We are good. We're good to go. And we know that the device is in saturation. Another way of thinking about, even though the drain voltage is below the gate voltage, right? So remember that the drain voltage can come below the gate voltage by as much as 1 threshold before we reach the edge of saturation and triode region. So the drain is lower than the gate right now by only 0.2 volts. It can be lower by 0.5 volts. Okay, so we are in saturation. Good. We go ahead and calculate everything. All right, we have to calculate GM and RO to find the small signal model. GM has 3 equations. Which one do I use? It doesn't make much difference, but given the numbers that I have right now, I have at the overdrive voltage, I have mu and C aux. Sorry, I should have said we also have W over L. Let's assume 10. Then I will write it like this. I will say mu n C aux W over L VGS minus VTH. That was one of the equations that we had, right? So you plug in these numbers, and what we obtain is GM is equal to 0.7 millisiemens. And you can also just invert this and write in terms of ohms. So we get 1 over 1.43 kilo ohms. This is a relatively low transconductance for a MOSFET. Typically, in our designs, the transconductances will be higher than this, or this resistance will be lower. So we are looking for maybe a resistance of a few hundred ohms. So that's the typical value. All right. Okay, so we found GM. Good. That's done. Now we go to RO. RO was 1 over lambda ID. So RO is equal to 1 over lambda ID. ID is the bias current. I can find the bias current because I know how much bias voltage I have here and here. So I can go ahead and do that. How much is ID? So ID is equal to 1/2 of mu n C ox W over L VGS minus VTH squared. Should I write 1 plus lambda VDS? Well, the true ID, yes, is equal to that. But remember what went into here? Didn't have 1 plus lambda VDS. So I just write it like that. Because I'm only interested in placing this ID here. That's it, right? So we write that as, we calculated, it comes out to be 0.245 milliamperes. And given that lambda is 0.2 1 over volt, we have RO equals 20.4 kilo ohms. All right, we have found the small signal model of the transistor under these conditions if W over L is chosen to be 10, for example, 5 microns over 0.5 microns, something like that. All right, before we leave this example, I want to draw your attention to one interesting point. If we multiply GM by RO, that GM times this RO, it's not related to small signal model, but just something on the side for your own information. GMRO is about 14 in this example. So what's interesting is that GM times RO, which seems just to have fallen from the sky. You have no idea why I multiplied GM by RO. But for now, just take it, is relatively large compared to 1. So we can say GMRO is much greater than 1. What does that mean? Why are we talking about that? Why is GM multiplied by RO? We don't know at this point. Just remember that for the future. Very well. That was a quick example on the small signal model. And now we can go to a different type of MOS device. The MOS device that we have studied so far is called an N-type MOS device. So let's write this out. So MOS device types. So what we constructed was this. We had a conductive gate on top of oxide. Then we had a substrate which was P-type. Remember, the first time I introduced the MOSFET, we had a second plate of a capacitor which was built out of P-type material. We saw that in these MOS devices, we have an N+ region for source and drain, and this P substrate here. And this is what we call an N-type device, or an NMOS. So the question is, can we build a P-type device, a PMOS device? Well, yes. Why don't we just flip all of the signs and polarities and see what happens? So we start out with the second plate in an N-type material. So this is an N-type material, N substrate, if you will. And then we place a P+ region here, another P+ region here. So we still have a gate and a source and a drain, but everything is flipped. Okay, so previously we said if the gate is positive enough, it attracts electrons to this interface and they begin to conduct current. In this case, if the gate is negative enough, it will attract holes to this interface. So we will have a bunch of holes here, H, 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 and they create a channel. The channel in this case is made of holes rather than electrons. All right, so we see that the gate has to be negative with respect to the source. So we say VG has to be less than Vs. By how much? By one threshold, right? The concept of threshold still applies, meaning that as we make this gate more and more negative, first we create positive ions, but eventually we attract holes. So that is the threshold voltage. All right. Is the threshold voltage negative? Yes, because this gate has to become sufficiently negative compared to the source. So the threshold voltage is also negative. All right. Now, we have created holes between source and drain, and we need to conduct a current. So how do I choose the polarity of the voltage difference between source and drain? Well, I want the holes to start from the source and go to the drain, right? So that means that the source has to be more positive than the drain. Again, in contrast to what we had here. In this case, the drain was more positive than the source. So the source the drain has to be less than the source. All right, or VDS has to be negative. These are the conditions necessary for this device to conduct current and become a voltage-dependent current source or something like that, as opposed to the voltages that we had around the NMOS device. So this is what we call a PMOS device. Now these values are not as intuitive as what we had in the case of NMOS, but we have to get used to them. In CMOS technology, we use both of these, PMOS and NMOS, and so we have to know both of them very well. All right, so we saw that the symbol for the NMOS device was like this, with an arrow pointing outward and representing the source terminal. For the PMOS device, we have a similar situation, except that the arrow points inward. This is how we distinguish between PMOS and NMOS. Okay. All right, so let's go ahead and apply these different voltages around this guy to bias it up. Right? We want to turn it on. So I need the gate to be more negative than the source. So the gate has to be more negative than the source. So negative, positive. The drain has to be more negative than the source. So the drain has to be more negative than the source. And these are different from what we had here, right? We had positive between gate and source and positive between drain and source. Okay. Now remember that in electronics, generally, we would like to show our more positive voltages on top of the page and our more negative voltages on the bottom of the page. So in that regard, we typically flip this upside down. And we draw it like this. We put the source on top, put the drain on the bottom, and the gate over here. And then, for example, we have a battery between source and gate. The gate has to be more negative than the source. We have a battery between source and drain, and the drain has to be more negative than the source. So we often draw it like that, just for consistency with our general convention for drawing circuits. Not a big deal, you don't have to do it that way, but often we do it that way. And therein lies a great source of confusion. Because if you're used to thinking that the drain has to be the top terminal from here, then you may automatically assume that this terminal is at the drain terminal. But that is incorrect. As you can see, this is the source terminal. So you have to be careful in this manipulation. All right. How do we define the drain current of a PMOS device? Well, you see that the holes are going from source to drain, which means the actual current, if we define it as current, positive current, is going from source to drain, right? But generally, we would like to look at the drain current as something that starts from the drain and goes to the source. That's what we did here, right? We said ID is this way. So we still use the same arrow, same direction. So we say ID is this way. But this ID is negative, right? Because the holes start from the source and go to the drain, which means if you denote ID in this direction, that would be a negative current. And that's fine, we live with that. Similarly here, ID is going this way, if you want to be very strict with your convention. Okay, so let's try to write the current equations for the PMOS device. Here we have to be careful not to get confused with various polarities. VGS is negative, VDS is negative, VTH is negative, so all of those have to be carefully included. All right, so what we write in saturation is ID is equal to minus, remember it's negative, minus 1/2 of mu n Cox W over L VGS minus VTH squared times 1 minus lambda VDS. So this negative sign was to be expected because we said the drain current of a PMOS device in this direction is negative. VGS minus VTH, we didn't fuss about them. Are they positive, are they negative? Doesn't matter because they're both squared. This difference is squared. So long as this is VGS and this is VTH, VTH is negative, VGS is negative, we are subtracting them and then we are squaring it. That's fine. But finally, this is a little strange. We have minus lambda VDS because VDS itself is negative. You can define lambda to be negative, but usually we don't do that. So it's really, lambda has a positive value, so I'll write it here. And then VDS has negative value. So this is our convention in this course. Now some books or some other courses may use slightly different polarities, different signs. You just have to be careful. But overall, the results can always be checked so long as you go back to these diagrams and remember where the actual current flows and what direction it has, etc. All right, this is the large signal model of a PMOS device in saturation, right? So the large signal model looks like this. We have a current source, and here we have VGS, gate, source, and then we have ID, and this ID is this equation up here. Okay, that's how we view it. All right, now remember that we had a pictorial view to see when an NMOS device is in saturation or triad region or at the edge. So we can repeat that for a PMOS device as well. So here's how we look at it. A PMOS device, we draw it like this. So I place the source on top because I would like to keep my positive voltages on top of the page. All right? Okay, so what condition places this in triad region? Well, here's what happens. If the drain is higher than the gate, by an amount greater than absolute value of the threshold voltage, absolute value of threshold voltage, because threshold is negative. So if you have positive, negative, and this difference is greater than the threshold, then the device is in triad region. This VDS, the magnitude of this VDS is too small. All right, so this is in triad region. I invite you to compare this with what we had for NMOS devices and see the similarities and the differences. All right, When does the device reach at the edge of triode region and saturation? Well, when this difference is exactly one threshold. So when the difference between these two is one threshold, then we are at the edge. And finally, if this difference is less than one threshold, in the magnitude of the threshold, then we are in saturation. So you can place these little dots closer to each other, right? I gradually reduce the vertical height between these two to indicate that the voltage difference is decreasing, and this is a difference less than the absolute value of the threshold. Then we are in saturation. Okay, so that pictorial view is always useful in case you have some complex circuit and you need to decide what's in saturation and what's in triode region. Okay, now we have a large signal model for the PMOS device. What do we do about its small signal model? Well, the small signal model is not that difficult. So let me add a page here. The small signal model of the PMOS device. Let me write that here. Small signal model of PMOS device. All right, so I will say this once, and I want you to memorize it once and for all. All right, this is very important. I don't use very often, but this is very important. So the small signal model of the PMOS device is identical to the small signal model of NMOS device. And I will underline this twice so that you remember. They are identical. So remember what we drew for the NMOS device, right? We said we have a gate source voltage. For small signal quantities, we call it V1 instead of delta VGS. And then we had, that's between gate and source. And then we had a current source here, which we call GMV1. And then if we want to include channel length modulation, we had a resistor here, RO. This model is exactly the same for NMOS devices and PMOS devices. There is no difference between them whatsoever. Now, you may be confused. You will be confused. Why? Because here's what happens. We drew our NMOS like this with the source on the bottom, usually, right? And that translated to this. Okay, so the gate, source, drain. Now, I come along and I draw the PMOS device. And as I said, typically we draw the PMOS device with the source on top. It's not required, but that's what we usually do. So here's a PMOS device with the source on the bottom. Now what do we have to do? Well, if you're still thinking that the top terminal is the drain, you will draw the small signal model incorrectly. You have to remember that this is the source terminal. So this model has to be drawn upside down. So here's how it goes. Gate, gate, source, source. A voltage between gate and source, plus minus V1. V1 represents a change, an increment. And then we have a current source that is directed from drain to source. Is directed from drain to source. And its value is still GMV1. V1 like this, with positive here, negative here. GMV1. And then, of course, if you have a resistor, RO, you have a resistor, RO. So you see that this model and this model are identical. I flipped it over simply because the symbol for the device was flipped over in the circuit. If you did not flip this over, you would not flip this over. It's the same thing. The source of confusion can be that you look at this arrow, it's pointing downward. You look at this arrow pointing upward. You say, ah, well, that means that one of them is positive, one of them is negative. That is incorrect. These are exactly the same thing, except that we drew it upside down because this was upside down. That's all. So please remember that. I know I have seen hundreds of students who have made this mistake. All right. Now that we have the small signal model of the PMOS device, we are ready to look at a quick example. So let me go over here. I will give you a circuit, and we want to draw the small signal model of the circuit. We don't know what the circuit does at this point, and that's okay. So here's a PMOS device called M2, an NMOS device called M1, and we have a microphone here, a battery here, a battery of value V0, another battery here of value V1. And we would like to draw the small signal model of the circuit, including everything, channel length modulation and everything. And we assume that this microphone can be modeled by a simple time-varying voltage source called Vin, like before, right? Okay, so again, we start from the left and replace everything with this small signal model and go forward. So, microphone becomes a voltage source, very good. The battery doesn't change with time, becomes a 0 voltage source, so a short circuit. The NMOS device, sorry, I have to leave more room for myself, so let me bring this down. So here's the microphone, Vin. The M1 has a gate here, a source here, so that is the gate and the source, whose difference we call V1, according to the small signal model here. And then we have GM. Now I have two devices. They may not have the same GM, so I'll call this GM1 V1. And then it may have a resistor, output resistance, so RO1. That is the model of M1. The source terminal goes to this general rail here, and it's actually connected to here because the battery was replaced by a short circuit. So that goes here. All right, let's go to M2. M2 is drawn upside down, so I have to draw the small signal model upside down. It has a gate. The gate happens to be shorted to this gate. So just go up here, and we have a gate here. This is the gate of M2. It has a source up here, so that's the source. And we have a voltage between the gate and source, a small signal voltage, an increment, which we denote by some sort of a lowercase letter. But we don't want to call it V1 because V1 belongs to this guy. So we'll call it V2. So V2, positive here, negative here. Again, remember, positive here, negative here. Positive here, negative here. This is just drawn upside down. And then we go and we draw the small signal model of M2 as a current source, pointing from drain to source. Pointing from drain to source. Exactly the same thing. GM of the device, GM2, times its gate source small signal voltage, V2. And then an output impedance, if we wish to include channel length modulation. So here's RO2, and this is connected to the drain. So that's the drain of the PMOS device. This is the drain of the NMOS device. And it just happens that they are shorted, so we short them together. What else is left? Well, we have a battery here, and the battery is replaced by a short circuit. So that goes right like this. This is the small signal model of this circuit. All right. Okay. We can make some simplifications if we really try to in this model. Because if I want to analyze this, I have to write a bunch of KVLs and KCLs, node equations, that sort of thing. But rather than jump into calculations, I take a step back and see, can it be simplified? Well, look at V1 and V2. Are these two voltages equal? Yes, because V1 appears between this node and this node. Positive here, negative here. V2 appears between this node and the same node. So V1 and V2 are equal. That's pretty good. All right. Is this current source in parallel with this current source? Yes. This current source goes from this node to here. This current source goes from the same node to here. So these two current sources are in parallel. We know that if two current sources are in parallel, we can add their currents and represent it by one current source, right? So that's interesting. How about these resistors? Are they in parallel? Yes, because this terminal is shared with this terminal, and this terminal is shared with this terminal. So they're in parallel. So suddenly, this very complex circuit can be simplified to something nice and easy to handle. Our job at this point is not that. We will come back to that sometime later. But my point is that anytime we draw a circuit, we have to see if we can simplify it before we start writing equations for everything. All right, our time is up. I will see you next time.